Welcome to another stream, everyone. Today we're looking at Year 12 Methods class, and we're going to be looking at exercises 9.3 and 9.4. But if I can get you to just say hi in the sector forum, as always, and if you want to have a try and guess of the background that I'm in today, the place that I'm in, you can do that. Let me just do a couple of things, and we're good to go. Alright, so we've got 2 viewers at the moment, so as I said, if you can just make sure you say hi in the sector forum, we'll start the lesson very soon when it gets to 9 o'clock. And if you want to also guess the location of the background that I'm in, please do that as well. So we'll start very soon when we get to 9 o'clock. So far we've got Michelle and Andre in the sector forum. Hannes says hi. Josh, Johan, Guy, cool. We've got a few people here. Hannes, Johan, cool. Alrighty, so more and more people are jumping on right now. We've got 7, almost got half the class. And it's almost 9 o'clock. Well, it is 9 o'clock, so let's get into it. If I get into that screen, and here we go. Okay, so today we are looking at 2 chapters or 2 exercises. So we're looking at exercise 9.3, which is to do with the area between curves, and we're also going to look at exercise 9.4, which is we will look at area functions again. So today what I thought we'd do is start by looking at the area of composite shapes. So we know how to work out the areas of composite shapes way back in years 8 and 9. You would have learnt this stuff, maybe even in year 7, where the idea being if you wanted to work out the area of this shaded region, you would first of all work out the area of the outside or the bigger shape, and then you take away the area of the inside, the smaller shape. So we're going to apply that same idea when we're working out the area between functions, between curves. So here we've got kind of like a general example. So here we've got 2 functions. We've got this red function here, f of x, and we've got this blue graph here, g of x, and we're trying to work out the area that's shaded between the 2 graphs, okay, this kind of creamy colored color. So the way we're going to do it is we're going to think about it in terms of composite shapes. We're going to first work out the area underneath the red graph, which would cover all this section here. So that would cover the region that we want plus this white space that we don't want. Okay, so that would be the integral between a and b on the x-axis of f of x. But then if we want to take away this white space that we don't want, then it's just a simple case of just taking away the integral of g of x between a and b. And we can just do this all in the one integral. We don't need to split it. We can just go between a and b of our 2 functions taken away from each other, subtracted away from each other. So this integral here that we've got in our general example represents the area of this shaded region. And the way we do it essentially is we do the integral of the top graph minus the integral of the bottom graph. So it's the top graph minus the bottom graph gives us the region that we want, okay, or the area between the curves. Okay, so I'm going to do 4 examples today to cover this, and each one I'm not really going to be specifically concentrating on the actual substitution aspect when we're doing the integration part. So that bit I'm going to go over pretty quickly. It's more a case of making sure the integral's set up correctly and making sure the order of the functions in our integral is correct. Okay, so this first one says calculate the area of the region enclosed. So that's another word you're going to see a lot in this exercise. So enclosed is meaning just in between, by the curves with equations y equals x squared plus 1 and y equals 4 minus x squared, and the lines x equals -1 and x equals 1. So I've got some steps here. The first step is I would like you to draw a sketch of the graphs and the lines to see what's going on. And the other benefit of drawing a sketch is to see which function is on the top and which one is on the bottom, so you can get the order in the general rule correct. And then once you've got your sketch, you want to apply the rule, which is the area of the enclosed region between the curves is going to be the top graph, f of x, minus the bottom graph, g of x. Okay, so top minus bottom, all okay. So if you wanted to pause the video and try this question for yourself, I'd really encourage you to do that. In the meantime, I will keep going with the live stream. Okay, so here is the situation we've got. Here is the sketch of the 2 graphs. Okay, so in red, I've got the y equals 4 minus x squared graph, which is this one here. And in blue, I've got y equals x squared plus 1. And the 2 dotted lines are our x equals lines. So x equals -1 and x equals 1. The region that we want to work out the area is just in this section here. Okay, so essentially what we're trying to do is work out the definite integral between -1 and 1 of our top function, our top graph, which is 4 minus x squared, and we want to take away the bottom function, x squared plus 1. So one of the benefits of doing it this way is that you can do some quite simple algebra, just simplifying this section here before you do any anti-differentiation. So it's just a case of 4 take away 1 is the 3, and -x squared take another x squared is -2x squared. So that just makes our anti-differentiation process a lot easier too. Rather than having to anti-differentiate each of these terms, which you can still do, it just makes it a lot easier to simplify the terms first. Once you've done that, then it's a case of just applying the basic reverse power rule, which is add 1 to the power, divide by the new power to the terms. That's anti-differentiating it. And then, of course, we're going to substitute in the upper and lower bounds of our problem. Excuse me. So the upper bound was x equals 1 and the lower bound was x equals -1. So substitute them into there. And as I said today, I'm not going to focus too much on the substitution part today. More a case of making sure our integral's right and simplifying it's right and getting the right answer in the end. Okay. So this ends up being an area of 14/3 square units. And as I mentioned in previous videos, when we're dealing with area questions, we need to make sure we include the units. And if there's no unit specified in the problem, we just write square units or units squared, like some people write. They write out the word units and then put a little power 2. Okay, here's a second example. This time it's find the area enclosed by the graphs of f of x equals x to the power 3 and g of x equals x. So again, my first step would be to sketch the graphs, and that really gives you a good picture of what's going on. And this time we're interested in some intersection points. Okay, so what I mean by that is, if we sketch the graph of the two graphs, we've got the x cubed graph, which I've got in blue over here, f of x equals x cubed, and the red graph is g of x equals x. Okay, so the main things is x cubed and x. They're our 2 functions. We're interested in the intersection points here because you can see that the graphs cross over each other. Okay, so the graphs cross over each other here at the origin and then again at 1, 1. Okay, so they cross in 3 points. So at the origin 1, 1, and they also cross over here at the very beginning. So the area enclosed is these two sections here. And it's important to get the intersection points because for this first section, you can see that the blue graph is the one that's on top and the red one is underneath. So we need to make sure the order in our integral is correct. In the second part of our graph, you can see that the red line is now on top. It's the graph higher on the graph. And the blue graph, the x cubed, is now underneath. So what does that mean? What we need to do is we need to split this problem into two integrals. One to work out this bit and one to work out this bit. And the reason why we need to split it into two because the functions are kind of being replaced with each other. What I mean by that is they cross over each other at those points, and so we have the blue function on top to begin with here, and the red functions underneath. That's why it's in that order. The order is really important. The top function must go first, and the bottom function must go under afterwards. And the integral for this first one goes between -1 on the x-axis and 0. We're not interested in the y values here when we're anti-differentiating with respect to x. We're only interested in the x values of our integral. So between -1 and 0 for this first section, f of x minus g of x, and then we're going to plus because we're adding these two regions together. The integral between 0 and 1, x equals 0 and 1, of g of x, which is the red graph, minus f of x, which is the blue graph. Okay, so if you wanted to pause the video and substitute these functions into the definite integrals here and try and work it out for yourself, please do so. Please pause the video and work this out for yourself. You learn more by practicing and by doing rather than just watching, okay? All right, so hopefully you've had a bit of a chance to do this question, and here's the solution to it. So all I've done here is I have substituted in the blue function, which is x cubed, and the red function, which is x, in those points in our integral. And then it's just a case of anti-differentiating each of the parts, and then substituting in the upper and lower bounds of each of the integrals. If you've done it right, you should end up getting 0.5 square units or half a square unit. Now, some of you might be inquiring, can you do this with a calculator using the absolute value function? And you can. So rather than splitting it up into two integrals and working out each one separately, the calculator's got the inbuilt cas function. So what we can do is we can work out the absolute value of the difference of the functions, and notice it's just the one thing. We're just going x cubed minus x, and we're going between -1 and 1. So we're just basically doing the whole thing. We're going between -1 and 1, and we're saying x cubed minus x, the absolute value of that. And the order that you put these actually doesn't matter when you're doing the absolute value function because any negative parts will just calculate as positive anyway. So if you are allowed to use calculators for these type of questions, then you just use the absolute value function. And remember from the last video, don't put the absolute value function on the outside of the integral, put it on the inside of the integral where you've got your function, okay? Third example, I'm going to deal with some trig functions here, okay? So we've got find the area of the shaded region, and this time I'm not going to give you much more of a hint than these two here. So find the intersection points, the x values of these two graphs, and then try and give this a go for yourself. So you've done 2 examples so far. I've done 2 examples. If you haven't pressed pause so far in the video and tried to do these questions yourself, give this one a go. Challenge yourself. See if you can do it. Okay, so hopefully you've given this question a go, and here is the solution for this problem. The first thing you want to do is you want to work out the intersection points. You're basically working out when is sine x equal to cos of x. Okay, so you can think about that in terms of your unit circle, You can think about that in terms of just your exact value knowledge, but sine x and cos x are equal to each other at 45 degrees, or pi on 4, and 225 degrees, or 5 pi on 4. What I will say is it's really important when dealing with calculus and trig functions, you must have everything in radians, okay? So don't deal with angles in degrees here. Everything must be in radians when dealing with trigonometry and calculus. When we're trying to work out areas and differentiation and that kind of thing, and gradients, everything must be in radians. So here we've got the problem, okay? So this one, the intersection point there is at pi on 4 and at 5 pi on 4. So here's our definite integral setup. Remember, the top graph in our function is the bit that we start off in our integral. So sine x is the graph on the top, and on the bottom is this cos of x graph in red. And notice I've used colors here to try and illustrate that. So next up, now we just go through the process. We've set it up, and now we do the antiderivative of sine x and cos x, and that's what that becomes. So the antiderivative of sine x becomes negative cos x, and the antiderivative of negative cos x becomes negative sine x. And again, we've got the upper and lower bounds that we substitute into these things, and you end up getting all these 1 over square root 2, or 2 square root 2 on 2 if you rationalize the denominator. I just rationalized it at the very end because it was convenient, and for this one you end up getting 2 square root 2 square units as the final answer, as the area trapped between these two trig function graphs. Okay. Finally, the last example that I want to talk about comes from the OTLE textbook. I think it's question 1I of exercise 9.3. And this one just has a little bit of a difference in it to talk about. All right, so in this one here, I've got 2 linear graphs and a parabola, quadratic. And we're wanting to work out the area enclosed in this region here, this kind of gray-black colored in section. All right, so the way we're going to do this is the first thing we want to do is work out the intersection points. So obviously it looks very clear that the intersection points of these two blue and red graphs cut at 1, and they do. The other point that's really important to us is right up here where the parabola and y equals x intersect. So we need to work out the x value at that point. Don't just assume, don't just guess what it is. We actually have to use algebra to work it out. Okay. Then what we're going to do is we're going to split this region into 2 parts. And the reason we're doing that is we've got the area trapped, and I might just draw this in here. So I'm just drawing this little red line in the middle here to say we've got this first region here on this left side, and that's the area trapped between the blue line and the red line, okay, between x equals 1 and x equals 2. But then on the right side, in this section here, we have the area enclosed between the blue graph and the black parabola, just in this section here. So we'll need to set up 2 integrals again and work out the area of this section, and then work out the area of this section, and then add them together. So here we go. We've got the integral between 1 and 2 of f of x minus g of x, so the blue graph minus the red graph. Then we're going plus the integral between 2, and we don't know what that x value is just yet, you'll need to work that out, of the blue graph and the black graph, f of x minus h of x. So I'm going to pause the video again, or I would like you to pause the video, and I would like for you to give this problem a go and see if you can get to the answer, and I'll go through the solution in a minute. Okay, so here is the solution to this problem. So when we solve for the question mark, the x value that the blue graph and the black graph intersect, it's just a case of solving the 2 equations equal to each other. X equals 2x squared minus 4x. Solving those equations and collecting like terms, you end up factorizing out the x to help get to your solution. You get x equals 0, and you get x equals 5 over 2. If we go back to the graph, we can see that x equals 0 is where the graphs cross over at that point there at the origin, but the 5 over 2, the 2.5 is where the graphs intersect, the x value of where those graphs intersect, which is what we want. So now what we're going to do is we're going to set up our integral. This time all we've done is replace the question mark with 5 over 2, and in the next line all I've done is I've replaced each of the blue, red and black functions with their actual equations, what they are, and so, or expressions. And now we're going to simplify. It's always best to simplify the terms before anti-differentiating. So in my integral here, don't anti-differentiate from this point. Simplify the terms first to make the antiderivative easier. Okay. Similarly over here, I've got x minus negative 4x becomes 5x. Take away 2x squared. Do the simplifying first to make the antiderivative easier. Next up, it's just a case of doing the antiderivative of each integral, substituting in the upper and lower bounds, and simplifying to get your answer. So in this one here, we end up getting a final answer of 37 over 24. Again, remember the square units as your measure of your units. Yeah. Okay, final thing I've got here is the exercise questions for you to do, to practice in exercise 9.3. So it's on page 96, giving you quite a bit to practice. But again, what I want you to focus on is getting the order in the integral correct. So top graph minus bottom graph. Sometimes, just like that last example we just did, you'll need to split it into separate regions and work out the areas of each region and then add them together. Okay, so at the very beginning I talked about composite shapes. This is really an extension of this idea that you learnt back in year 8 and 9, where you started with just normal shapes. And what this basically means is you can work out the areas of just about anything using calculus. Okay, those of you doing specialist maths will go on and do volume of revolution. So you'll look at things like the volume of three-dimensional shapes as you rotate these 2D objects around the x and y axes. I think that's it. There is one example in the textbook that deal with the area trapped between the curves, and it's in relation to the y-axis. So we might cover that in a Teams chat later on. But I'm going to go over now to exercise 9.4. I'm switching things over. So we're going to cover 9.4 today as well. Just get this one ready. And we'll get straight into it. Here we go. So exercise 9.4 covers area functions. And we had a bit of a sneak preview to this earlier when we covered exercise 8.2. When we looked at the rate of change of these area functions, and in particular it linked to the fundamental theorem of calculus, the second version of it, the second fundamental theorem of calculus. So all I've got here is just a kind of a quick refresher, and then we'll look at the types of questions we have to do in exercise 9.4. So here we've got our function f of t. This is just straight back from the notes from 8.2. Just got a random graph here. And this area function that I'm talking about is this region trapped underneath the graph. And imagine this x value is moving anywhere between a and b. As it moves from a to b, it creates this area function, okay? So we can model how much the area is increasing and decreasing, that kind of thing, when the area is maximum, when it's at a minimum, and it's more a case of when we have functions that go below the x-axis. The area function is going to have positive and negative integral aspects to it. So sometimes the area function will equal 0 because that's when the area above the x-axis in the curve and below the x-axis in the curve are equivalent to each other, and those integrals, those area bits, cancel each other out. And so that's what we're going to be looking at in this exercise. So I've got a couple of examples. At least an example. I think I've got one today. Be nice and quick. So let f of t be our area function, and it's going between -4 and t, somewhere along the x-axis, somewhere t is. This is our straightforward function. It's 2x minus 4, just a linear graph, where t is somewhere between -4 and 8. Okay, so we're starting at -4 and we're going to 8. Without a calculator, find f of t, which is the original function, and hence capital F of -2 and capital F of 8. So the first thing we're going to do to find f of t, capital F of t, is we're going to calculate the definite integral of this thing. Notice this is all in terms of x's and not t. So we're going to work out the definite integral, and what that means is when we anti-differentiate it, we're going to substitute in the upper and lower bounds into our antiderivative, and that's going to give our capital F of t function. It's going to have everything in terms of t. So here we go. The antiderivative of 2x minus 4 is going to be x squared minus 4x. Notice it's still in terms of x's. So what we do now is we substitute in the upper bound t and the lower bound negative 4 into our antiderivative, and you get t squared minus 4t when we put the t in. And then we take away 16 plus 16. That's when we substitute the negative 4 into our antiderivative. And then we simplify this, we get t squared minus 4t minus 32. Notice we didn't have to worry about a constant or anything here, because if we had a plus c in our antiderivative, it would be in this section of the brackets and in this section of the brackets, and the c's will cancel each other out. Final part of the question says, hence find capital F of negative 2 and capital F of 8. So that just means substitute negative 2 and 8 as our t values in our f of t function. It's pretty straightforward. So when we substitute negative 2 in, we get negative 20, and when we substitute 8 in, we get 0. So our area function drops to negative 20 when the t value is at negative 2, and the area function is 0 when we get to 8 on the x-axis. So the next part of the question says, solve for t if f of t, capital F of t, equals negative 20. Well, we kind of got one already. We got this one here. We got negative 2 as one of our answers. But let's just do this properly, because there might be more than one answer. So to do this, all we're going to do is get our f of t function, which is t squared minus 4t take 32. It's this thing up here that we worked out earlier. It was the antiderivative of what was inside the integral. And just solve it equal to negative 20. It becomes a quadratic equation. Factorize if you can to make it easier, because we have to do this without a calculator. And we end up getting t equals negative 2, which we knew from our substitution just a second ago, just here. That's t equals negative 2, gets us negative 20. So we knew that one already. But we end up getting this one as well, t equals to 6. Okay, so we get negative 20 for our area function 2 times. I'll just pause a second and talk about why we have an area function and negative areas, and I've said before it's always positive area and stuff like that. So the reason why our area function is getting negative values is because this is just an integral, okay, and an integral can give negative values, okay. So it's up to us to be able to, when we're asked to work out the area trapped between curves or underneath the curve, what we need to do is interpret that negative integral and turn it into a positive value, okay? But area functions, in this instance, can be dealing with negative integrals, and that's okay, okay? So it's saying some parts of the graph go below the x-axis are going to give us negative integrals. So my point is, don't convert these to positive values for area function questions. Okay, so we've done part B. Then the part C, this is the bit that's a little bit new, is where we're asked to work out the global minimum and the global maximum values for f of t. Okay, so for our area function, when is our area function the biggest and when is it the smallest? In particular, we're asked to work out the values here. So not necessarily the t, the time, or the t values on the axis when it happens. It's saying, what are the global minimum and maximum values? So what's the biggest function area part and what's the smallest area? And these questions, you can get negative values, okay? So the minimum, it might be a negative value. We already got negative 20. It might be even less than that. We'll see. So these are the steps to solve these type of problems. Because we're dealing with minimum and maximums, think of our area function as something that we need to optimize. So if we're trying to optimize it, we're looking at when the gradient of our area function is equal to 0. So this is what this is. We're solving for when the derivative of our area function is equal to 0, and that's going to help us find these minimum and maximum points. Then we have to check the nature of when we find the t values for when the derivative is equal to 0. So that nature means check for if it's a maximum or a minimum, and for that we can just do the second derivative test most of the time. And the final thing we need to do, because it's asking for global minimum and maximum values, is we need to check the end values of the domain. We have to substitute -4 into our area function and 8 into our area function, and just compare that with everything that we've discovered so far about the local minimum and maximum points we could potentially find with solving the derivative equal to 0. So if you wanted to give this problem a go, try it for yourself, please pause the video and try this question. Otherwise, we'll go through the answer right now. So solving the derivative of our area function just means, remember, if the, let's go back to the question up here. If f of t is our antiderivative, then our derivative is going to be this thing that we had to start with. Okay, but in terms of t. But if you still wanted to differentiate this thing, you could. So it's going to be 2t minus 4. But that's essentially what we're doing here. Okay, so solving the derivative equal to 0 in terms of t, of course, is going to be 2t minus 4. Solving that, you end up getting t equals to 2. And when we substitute that t equals 2 back into our f of t function, we end up getting -36, which is quite a bit smaller than -20. So this looks like it could be our potential minimum value, but we have to still test. The next thing we're going to do is do the second derivative test, just to make sure what type of maximum or minimum this t value is. So when we do the second derivative, the derivative of this, we end up getting 2. And since there's no t values in this second derivative, this is always going to be greater than 0. And the second derivative test says if your second derivative is greater than 0, then it's going to be a minimum point. It doesn't tell us if it's a global minimum or not, so it doesn't tell us if it's the smallest point in the domain, but it gives us a clue that it is actually a minimum. Okay, so the next thing we need to do is think about the maximum values that we had, and there was no local maximums because we didn't get any derivatives equal to 0 other than just this one here. So this comes back to, let's substitute in our the end points, the end values of our domain, to get an idea of some other coordinates, some other values that we are interested in. So f of -4, if you substitute -4 back into our f of t function, so back into this thing here, t squared minus 4t take 12, you end up getting 0 for that one, and f of 8 is also 0. But let's just talk about this one here, okay? Think about what we're actually doing at this first bit. We're working out the area function at the very beginning, all right? So what I'll do is I'll scroll all the way up to this graph here. So the area function is looking at the area underneath the curve. And if you're looking at the area function right at the very beginning, this first point that we substitute into it, okay, you're essentially working out the area of a line at the very beginning. And that's always going to be 0 for these area functions, okay? So if you are working out the definite integral between -4 and -4, the starting point, it's always going to be 0, all right? So this is why when we check the initial endpoint, we're going to get 0. This one, it depends on the actual function. Like if the graph is symmetrical, okay, so if it's absolutely symmetrical, I have half the graph above the x-axis and half of it below the x-axis over the domain, then the area function is going to be 0 here as well, because half the region is going to be a positive integral and half of it's going to be negative, and the area function will balance those out, cancel each other out, okay, which is what's going on in this problem. Finally, we have to answer the question. So the global minimum value we discovered from doing the derivative was -36, and the global maximum value we got from, because there wasn't any other derivatives equal to 0, there was no other values to test, the global maximum values we got from substituting in the end values, and we got 0. That was the highest it ever got, okay? That is it for exercise 9.4, the explanation to it. For practice, what I'd like for you to do is just do the odd questions. in here. There's a really good example in the textbook as well, just before the exercise starts. It has a slightly more difficult function than what I did in this question here, but in the exercises they don't have anything that difficult either, to be honest, for 9.4. But have a go at those questions that I've listed down here. I'll go over it again. And that is it for the live stream. We're going to go over to Microsoft Teams now, and I'll set up a group call. And if you've got any questions about what we've learnt today, you can ask them there. Okay, thanks guys. That's the end of our stream. It's the last one for the term. I wish you guys to have a happy and safe have a safe Easter break, and we'll look forward to seeing you all next term. See you guys.